Good afternoon. Welcome to today's webinar from SCA with Dr. Robella Samuel on Drillstring design and drilling optimization with mud motor operation. Before we start today's webinar, we'd like to ask a few questions about the demographics of the audience. So please check your control panel to see polling questions. The first questions we are distributing are: what are your primary disciplines? We have petroleum engineers, geoscientists, facility engineers.
I changed that.
Okay. So we are, looks like about a third petroleum engineers, a third geoscience, and a third others. So the next question is, how many years of full-time experience do you have? Less than a year, 1 to 10 years, 11 to 20, 21 to 30, or over 30 years. Looks like we have a lot of people in the middle group. About half of you are in the 11 to 20 years. We'll close this and share the responses. And then our last poll is, what's your primary discipline? Oh, it looks like this is a repeat of the previous poll. So I will proceed with the introductions. And before we commence, I'd like to remind the audience today that you are muted throughout the entire conference, so you can ask any questions during the presentation using the GoToWebinar question feature. We'll cover the Q&A at the end of the presentation, and you will be anonymous. So let's move to our introductory slides here. This is a webinar on Drillstring design and drilling optimization with mud motor operations. And Dr. Samuel has been a Chief Technical Advisor and Fellow with Halliburton since 1998. He has more than 30 years of experience. He's received several awards from SPE. He's taught at a number of universities in adjunct professor appointments. He's very well published with over 200 technical papers, 67 patents, 4 patents pending, and several books. He serves regularly as a keynote speaker at conferences around the world. And so you'll get a little taste of the class that he's teaching for SCA this year on principles and practices of mud motor, offered in May in Houston and in September in Midland. If you want more information, please contact us. We have public courses, or we can always offer these classes in-house at your own location. And of course, SCA, in addition to training, we provide consulting, direct hire, and projects and studies. And so I'm going to send the presenting rights over to Dr. Samuel. Let me change presenters here. And please take over the presentation. Robella?
Yeah, thank you, Susan. In the next 20 or 30 minutes or so, I'm going to talk about under 3 categories. Excuse me. The broader topics of drillstring mechanics, associated drilling optimization, then mud motor operations. So the 3 components are important in designing a drillstring design. So now, in order to set the stage, I wanted to take you through a simple infographic on Eagle 4. A lot of information McKinsey has put forward, but I'd like to highlight 2. One is comparison of different fields in order to produce a billion barrel. So the famous field is Gawar field. You can see it is very close to that field. The next one is, if you think of, we have used almost 150 million foot of well path. So if we design more intuitively, we would have saved almost 2 million. It's a very small percentage if you take it. we can optimize it, and we can save almost 2 million of pipe. The second point is think of the drill pipe that would reach. It is told almost 1.25 times we can wrap around the world. That is equivalent to 165 million feet of casing pipe that has been used. We have put it down hole. Think of if we have optimized less than 1%, it will be equivalent to 2 million feet of casing pipe. If it is 1 million, 1% of pipe is damaged because of casing wear. It's almost 2 million foot of pipe. So now, moving on to the next one, can you relate the failures which you are seeing in these pictures? Twist off, burst, flaps, casing wear, the mud motors or rod failure, vibration failure, worn out stabilizers. What things happening? What are the things we can avoid? To the least, how can we mitigate some of the failures? That is going to be covered in this class. In order to understand completely, we need to have some basics. I would like to put forward some basics that are considered in drillstring design. One is a thick cylinder, the other one is thin wall cylinder. We have diameter, inside diameter, outside diameter, length, thickness. So we always measure in the form of D over T, that is slenderness ratio. Based on that, a thin wall and a thick wall is defined. If D over T is greater than 20, it is called a thin wall. D over T less than 20, it is thick wall. Now, how does it relate to our casings, tubings, drill pipes, and drill collars? You can see most of the casings we use, it stands from 10 to 35 D over T ratio. Pipe drill collars, we can see how it is. So it is almost 5:35 ratio. It goes from thin wall to thick wall. Then the second one is the aspect ratio. The aspect ratio is the length consideration. We deal with a lot of high aspect ratio system. You see aspect ratio is length over diameter. L over D is very, very large. Say, take 40,000 feet of pipe, it is almost 100,000. Now, so we deal with a diameter which is very small and a length very long. It's a highly oscillatory stochastic system that we have to design. That is the basic problem that we have compared to any other industry. So now, practically, we need to get some results. We need to understand how these results are obtained. One is the hook load. What are the forces acting along the string? What are the stresses? What are the limits that we deal with? What are the assumptions of the models that we have gone through? Then finally, failures. Can we avoid in the failure zone? Can we be within the failure zone? How do we avoid or mitigate? Now, in order to understand again the basic, not well understood system is the force calculations along the string. There are two forces. One is the true tension, the other one is the effective tension. So we deal with compression and tension as you see. Positive is tension, negative is compression. So we have the true forces which are acting in the string. If you put a strain gauge, we get actual forces are acting along the string. But we are not just dealing with that. We are dealing the system in a fluid-filled system. So we have to see the hydrostatic forces. So you can see here compression at the bottom due to the hydrostatic force. Now, if you take out the stability force, that we get the effective tension. Now, as I said, this is not well understood. We'll reinforce all these fundamentals in the class more in detail. And also considering the true and effective force, we have to deal with the limits. One is on the positive side, the tension limit. How do we obtain it? On the negative side, it is the buckling limit. How do we bracket those limits? What are the assumptions? How far we have learned in this space? That will be covered more in the class. Now, moving on to the next one, we have the torque and drag. Torque and drag calculation is one of the widely used calculations in our industry. So now we have to deal with the different operations like tripping in, tripping out, rotating on bottom, that is drilling, rotating off bottom, sliding, back careening, and rotating. And also that is including different mud properties with the surface pressure, annulus pressure, weight on bit. So the boundary conditions change. So how do we define the torque and drag under different operations? A lot of questions come up. In the traditional classic software, you don't find rotating on board, the string rotation and the rate of penetration for drilling operations. Why it is not considered? All these conundrums, paradoxes will be covered detailed in the class. Now moving on to the next one. When it comes to torque and drag models, there are several models. The well-known soft string model, which doesn't consider the bending stiffness. It is assumed it follows exactly the well path. So it aligns with the wellbore profile. Then the next one is the stiff string model, which realistically considers the tubular stiffness. And based on that, you will have different contacts. Now, if you have different contacts at the different points, you have different contact forces. So essentially, it finds the position of the string in the wellbore. On the contrary, soft string doesn't consider. What are the pitfalls in these two models? Now, always the stiff string model takes a lot of time because of the penalty in time in calculating multiple calculations and iterations for convergence. So now new model has been proposed, a hybrid alternating model between soft and stiff string based on the wellbore position and the string stiffness. Now we are moving on to dynamic model, transient torque and drag model for real-time calculations. How do we solve all these things? What are the different underpinning theoretical bases for these different models? What are the assumptions? What are the limitations? When to use it? How to use it? And the pitfalls that we have to study. Unless we know all these things, we may not be able to use effectively in our day-to-day design. So moving on to the next one is the failure, which is important. So it is a mechanical failure which we concentrate, which may be due to material failure or structural failure. When it comes to material failure, static, fatigue, dynamic conditions, most of the time we use static models. Then it comes to the material brittle and ductile. So you'll see on the left side, the signature of the stress strain curve is completely different. So the regular ductile theoretical models may not work for brittle casings. So how do we deal with all these different categories that are coming under the tubular goods? Now, we have to have a limit and an envelope that considers internal pressure, because we deal with the fluid, then external pressure, then real axial force that are acting along the string, then the string undergoes torque. Now we have to consider the burst condition, which is the positive differential pressure, then under the collapse for the negative differential pressure conditions, and also under axial loading. Now we deal with a lot of loads, and the properties change, not only based on the force, but also on the temperature. It starts changing, and we have to derate, and how far we can derate. We don't want to be very conservative in the design. We can put a lot of factors and to compromise on this. But how do we narrow it down so that we can save on the material cost? That we need to clearly understand. The limit curves are very important in the design space. Now, a lot of other topics that we need to cover, that which we will do it in the class. Pipe stiffness, how does it relate to the bending and the torsion? Friction, when we calculate the torque and drag, we use friction factor. Is it a fudge factor? Or it duplicates the Coulomb friction that we encounter in the traditional mechanical field. The neutral point. Neutral point, when, as we've gone through earlier, two tensions, true tension and effective tension, obviously we have two neutral points. Which neutral point to use, when to use it. Then bending stress magnification factor, when we use soft string, do we need to use it? Or when do we use it if it is a stiff string mode? So these are the conditions that we need to clearly understand when we use the bending stress magnification factor. Then it comes to buckling limit factor. Buckling is one of the complex tubular post-buckling process that we see, that we need to understand clearly. There are different models that have been validated in the bench of 50 feet or 100 feet pipes. How do we translate it downhole, which are tortuous? So the buckling limit factor, then bending stress ratio between the connections when we design the drill string, which is important. Then the stretch calculations. There are different stretch that the string undergoes. How do we calculate and how do we validate? So we will cover some other things based on the validated results. Then obviously we need to have the overpull calculations and the slip crushing since we use heavy load at the surface. Another important point that we need to consider with is the casing wear. Casing wear as we run the pipe, rotate the pipe, how far the casing is getting worn out. How do we degrade the casing properties based on the casing wear? So these are different topics that will be covered in the drill string design calculations and the analysis. With that, let me move on to the next topic on the optimization. Optimization and the drilling parameter optimization are very important. It is not only just designing it, but also we need to take it further in parameter optimization. So there are three things always we deal with: performance, efficiency, and optimization. As an industry, we get confused with these three terms, and we interchangeably use it without any underpinning. But they are completely different. But we will discuss mainly on the optimization. So before that, let's go through what are these terms. Performance. It is very simple. It is a metric that we can measure. For example, KPIs. It is a predetermined target that we compare against an actual, and also we adjust it based on as we go through the performance. So it is measurable. Obviously, it is achievable, which depends on the achievable metrics. Then we go on to the next one, that it is dependent on the relevance, right? If it is not relevant, there is no point in comparing it with. The next one is time. It has to be based on time because it changes. Now we have achieved a certain KPI, the benchmark KPI gets adjusted, and the next time it goes higher. Now, what is efficiency? It is a very simple metric, output and input comparison, right? It is the ratio output to input. For any operations, that is dependent on the output. depending on the efficiency, and we take risk, and it has to be more relevant to that. The next one is optimization. Optimization is clearly different. It is a mathematical technique to find the maxima or minima of certain functions like rate of penetration or the cost, subject to certain constraints. That depends on process, people, and technology. Clearly, you can see the difference between these three: performance, efficiency, and optimization. So a lot of things may change. Now, probably we may want to maximize rate of penetration, minimize mechanical specific energy, or minimize the cost. But we have to clearly understand the constraints in which we are dealing with. That the parameters, we get optimized parameters like weight turn rate, RPM, and flow rate are ultimately important. That it dictates the use. Now, different topics that are covered in the optimization topic is well planning, which is key in the optimization. Drilling rig has to be optimized. Well path has to be optimized. Well bore has to be optimized. Obviously, drilling fluids have to be optimized. Hydraulics, bit optimization, hydraulics, parameter optimization, then drilling parameters like weight turn bit and RPM, mechanical parameters, then well cost, then time, flat time. Now we are moving towards real time that can be coupled with analytics. So you can see we do optimization on its own, right, on a special topic, hydraulics optimization, which may be good. But sometimes we don't want into the silo trap, but we have to do a holistic system optimization that we need to consider with. That topics will be more covered in the class. Another one is how do we narrow it down on a single domain chart, which we can see here, weight on weight and RPM, torsional instability, lateral instability, where the vibration is an important one that we can map it. And also it is limited by the constrained maximum weight on bit and maximum rotational speed, depending on mud motor or rotary steerable or string. Then also it is constrained by ROP, and ROP is also dictated by the bit, whereas it is drilling, it is getting worn out. Then hole cleaning, that parameter involves on the flow rate. Then motor stall, if you are using motor, then we have an optimized stable region. So we'll draw these lines and find out exactly where our optimized region is. So comprehensively, we'll cover combining all the parameters in a holistic way in the class. That is an important one. Now, I'll take you one example. Most of the time we do hole cleaning or hydraulics optimization, the traditional optimization, nozzle optimization, impact force or hydraulic horsepower optimization, all these things. But is it valid when we do with the mud motor? Probably not, because it is completely different. The map you can see is completely different because the torque is dependent on the pressure drop, or the pressure drop depends on the torque on the mud motor. And also it is dependent on the configuration of the mud motor that we use. So you will see the weight on bit influence and the rate of penetration influence on the impact force, all the hydraulic horsepower per square inch. So it is completely different. Most of the time we use the same mechanical specific energy calculations, but it is dependent on the pressure drop, the torque, where in a regular one is purely a mechanical torque. Now this is dependent on the hydraulics of the mud motor. So that we need to clearly understand, that which will be also covered in the class. Based on this mud motor, let me take you through the mud motor in specific relevance. So mud motor is an important topic that we need to consider with, and let's go through the history. Lot of mud motors, downhole motors, impulse turbo drill, Russians are using a lot. They have used a lot single-stage turbo drill, multi-stage turbo drill. Then came the percussion hammers. Then PDM, positive displacement motor, which is commonly called the mud motor. That is the one which we use here. Then the electrical downhole motor. Purely it is run with electricity, but electric power, but it has not made inroads in our system as of now. Then miscellaneous downhole motors, several designs. Practically, it may be like a perpetual machine, which cannot be realized downhole. So, but we'll be concentrating only on the positive displacement motor. The question to be asked is why it is positive displacement, why it is called a motor. That we need to understand clearly. So it is a machine that which I call a workhorse, now becoming a racehorse, drilling very fast, coping up with the rate of penetration that we need. There are different power sections. We'll go in detail how these power sections are formed, what are the different types of power sections, what are the different types of elastomers, what are the different configurations we can see here, 3, 4, 5, 6, 7, 8, 9, 10 lobe configurations, and also how they develop different torques for different configurations, how they develop rotational speed for different configurations. You can see as the configuration increases, we have an increase in torque. As the configuration goes down, the RPM goes down. So how do we select an optimal configuration for our drilling conditions? How do we select a particular mud motor? How do we compare it with the theoretical values? There are different designs from use and throw to advanced design. Which one is going to perform better? All these things will be covered in the class, and also we'll go through specifications of different mud motors, how they fall into different categories, and how can we compare with another motor. So that we'll go through using a simple software that provides a quick and fast result. Then other things, the losses. How do we, even though it is called a positive displacement motor, they lose the efficiency. What are the failure issues like debonding, chunking, and when do you expect, is the pressure distributed uniformly across the cross-section? How the vibration is going to change when you use the mud motor against standard Drillstring design. All these things will cover in to a greater depth. Then the other one is the BHA design when we use mud motor. There are different motor configurations. Classically, it is called type 1, type 2, type 3, type 4 motor configurations. And what is the equivalent motor angle that we can use and calculate for the present conditions. And also, as we know, we slide and rotate. That also will be covered, and out of that we have a comprehensive operational roadmap. So ultimately I need an operational roadmap when I use it. A simple example is on the right side, rate of penetration versus flow rate. So do we change what is the optimum flow rate that I need to select when I slide, when I rotate? That is important. And also, what is the friction? How do we calibrate when I slide and rotate? Can I get some insights from the friction as I slide and rotate? How effective downhole the slide and rotation is getting translated? That all will be covered, that which I call the operational roadmap. That includes the torque and drag broomstick plot, power graph called the hockey stick plot, the stability plot, and more on the slide sheet. And also what happens when we pull out and run in for the swab and surge calculations. So this all the additional topics that will be covered in the mud motor section. Moving on to the next one, you will see the topics, power section, different designs, operational envelope, performance curves, the effect of pipe rotation. When we use mud motor, what is the effect of pipe rotation? What is the stability of the string with reference to the vibration? Now we rock the pipe. What happens? The effectiveness of the length that is being rocked. So it will cover additional downhole tools like agitators and mud motor combinations, and obviously the mechanical specific energy. I have covered the dynamics of the mud motor in the previous slide. And finally, repair and maintenance, ultimately, whether it can be relined, whether it can be discarded, or it can be used, what is the shelf life, all these things will be covered as an additional topic. So that the best part is you will get one of these books. When you attend that, you will see a lot of calculations, a lot of theory, and a lot of practical guidelines out of from all the topics that I'm going to discuss in the class. So with that, I would like to hand it over to Susan. Susan.
Great. Great. Thank you very much. I want to remind our listeners that they have an opportunity to ask questions using the GoToWebinar question feature. And so now is the time that you can start posting your questions. After today's webinar, you'll receive a link to the recording of the webinar, an evaluation form, a link to register for Dr. Samuel's class, Principles and Practices of Mud Motors, which is scheduled in Houston in May and in Midland in September. So we talked a little bit about the optimization and the mathematical models that are involved. What opportunities are there to use data analytics with optimization?
Yes, that's a good question. Now, we are more, as we get in real-time data, we can tune the model, because I discussed some of the factors that we use it. So that effectively, that can be modeled, that can be tuned in such a way that we can better predict. Purely science, we have a lot of assumptions, the physics-based model. Data science doesn't know the physics. We don't have the luxury of getting a lot of data from different sensors. So we have to combine in the way of hybrid approach. So both will handhold each other, then it will try to come up with the best model. That analytics will also be covered in a small portion, as I mentioned, on the real-time optimization.
Very good. As we're looking for opportunities to become more efficient in this day of lower for longer oil prices, where do you see the greatest opportunities for efficiency?
So that is already, I think, we are trying to achieve. One is maximizing the rate of penetration. The other one is minimizing the cost. That is one of the reasons the mud motors have made a tremendous inroad. They are very effective compared to other tools which are expensive, and ultimately that provides an opportunity for improvement. The mud motors have tremendously changed in the last 10 years on the design as well as the efficiency. And also we are trying to come up with a better wellbore, stable and integrated model that will provide a smooth wellbore. So ultimately, we have to produce, complete the well effectively, and produce in such a way that it can be long-term sustainable.
You mentioned sometimes there's an opportunity to, I guess it's refurbish a mud motor. Can you talk about some of the newer materials that are being used that can help them last longer?
Yeah, there are now elastomers have improved. Mainly, still we use elastomeric power section liner. So a lot of companies have come up with advanced material. And also on the other side, the rotor side, the coating has improved. So it doesn't get damaged. Right? So now we need to keep the mud motor for long hours. We don't want to change often. Right? That's, I think it is, we'll cover more in detail during the mud motor section. What are the different cross sections they have introduced, even wall and liners on the elastomeric side.
You focused on the PDM, the positive displacement motor, in this presentation. Are there times in which it is not appropriate, in which you would use one of the other types of motors?
If I understand the question, other types of mud motors?
Yes.
The turbines we use, traditionally Russians have used, and we are using a lot of turbines, but we use mainly mud motor PDM turbine for various reasons, the speed and the length and other things. We don't use it much, but there are some places we use it for shallow depth and for selective operations. But the mud motor provides what we need.
Are there any extreme conditions, high pressure, high temperature, different acid gas environments that might be a complication?
For mud motors, yes. Yeah, but
yes.
Now there are issues. We have seen mud motor failures due to the temperature from the interacting nearby wells, sudden spikes. The elastomer, which is the weakest on the material side, is having problems. But for the traditional shale plays, we don't have much problems. It doesn't mean we're not drilling high pressure, high temperature wells for that mud motor, but they can sustain high pressure, high temperature, obviously. Then the other issue is for underbalance drilling, they may not be effective, so we have to modify it. So there are different designs and considerations, and there is a sudden spike in temperature on the elastomer in some places where it fails. So the failure switches between the connecting rods and the bearings and the elastomers. Once it becomes stronger, then it moves to the other side.
And what is the latest in research that's being done in Drillstring design and drilling optimization? What's the new cutting edge challenge?
Now, with this high computing power, optimization has improved a lot. Now we can do real-time optimization at a much faster rate. As we pipeline new data, immediately we can come up with an optimized value. So the traditional static optimization has moved on to the dynamic side. Now the fundamental question to be asked is, are we happy with the soft-string model on the torque and drag? So now, do we need to move on to high fidelity torque and drag model that can provide a better optimization? Ultimately, this optimization precedes automation. It is not the other way around. Automation precedes optimization. Optimization has to be done in such a way that we can hand over the set points to the automated controls. So optimization is moving at a much faster pace. With a high computing power, we can do it at a multi-threaded, and that's what we are now moving on to the edge side, on the optimization.
To what extent does real-time optimization limit or prevent mud motor failures?
So now there are the instruments that the mud motors are run, trying to understand how they behave downhole. Most of the time, we use a performance curve, which are obtained under the ambient condition at the surface, fluid, viscosity, all these things. When it goes downhole, it is completely different. How do we understand downhole performance as opposed to the surface? Now, a lot of memory-based chips are placed to understand the vibration, the stability of the mud motor, how the pressures are distributed. That gave some insights, and the companies are modifying it in such a way that they are reliable. Now, how they behave downhole completely, because we don't have very good understanding. Sometimes it generates vibration. It is a source of vibration because it is rotating eccentrically. Sometimes we see heavy vibration. Sometimes we don't see it. Still, there are unknown parameters. But at least we have to understand, we have more understanding than what we have now than 10 years back.
So how often are the stiff string calculations used for torque and drag, providing the more realistic perspective as compared to soft string?
The industry is happy with the soft string last 30 years. Why? Because they are getting more dependable results as compared to the actual values. I have seen exactly it matches with an actual value, with a normal friction factor, 0.3, 0.25. You don't need to have a 0.5 or 0.8 to match with an actual data. On the contrary, it may lead to some failures because you have a high dog leg, which the soft string may not follow exactly what we are proposing it. But overall hook load calculations, you'll be okay. But when it comes to the stresses, you may fail. So sometimes we use the bending stress magnification over the soft string, so we have a better stress prediction. But what are the limits? When do you use it? You don't know. That is important. Then the soft string, when it is highly undulated, stress predictions on the position, we know exactly, right, based on the model prediction. That may not be an option with a soft string model. So now most of them, they don't use it because it takes time to calculate. Otherwise, soft string can give a better result. So now all the software companies, they provide it as an option. They don't charge additional charge. You get it, soft string, safe string. You compare it. When you get both options, why don't you compare it and take the best one? Now the new model is, why don't we use an alternating soft and stiff string? So soft string can behave as a stiff string in some of the wellbore conditions, and stiff string can also behave as a soft string in some of the wellbore conditions. You don't need a stiff string in certain portion of the wellbore. As long as you match the displacement and the forces, it should be okay. So you will have a better hybrid model, and you don't need to talk about soft string and stiff string anymore. That's the standard model that will provide better results. Now, another question to be asked for that question is, which one will predict a better casing wear, soft string or stiff string? Obvious result is stiff string. Stiff string will exactly get the contact points. Soft string is assuming it is going to wear out on the lower part of the casing. It doesn't track the multiple grooves, and it will end up in a conservative volume worn out. and you will be degrading it more than what it is supposed to be. So this is a complex system, and we have to selectively use it.
Yes, it sounds like there might be a value of information exercise in discussing the use of the stiff string versus the soft string calculations.
Yes, yeah, that will be more covered in that class. And they'll be doing an exercise and understand the basic theory behind it.
Very good. I want to remind our listeners that they have one more chance to submit questions before we close our webinar today. Later today, you will receive a link to the recording of today's webinar, an evaluation form, and a link to register for Dr. Samuel's class, Principles and Practices of MedMotor, scheduled in Houston on May 15th and in Midland on September 18th. So we want to thank you all for your participation today. And with that, we'll close the webinar. Goodbye.
Thank you.